Yeah, so we'll continue talking about integrals. So I just answered on the chat. It is the case that I think this stuff about integrals is considered harder for the majority of students when they take the class. So especially once we get to triple integrals, I think that's what really um, causes issues. For you, yes, the exam will be online, correct? Essentially, yeah. So the thing is that what happens is that for the next exam, there are classes, who have like in-person lectures or in-person recitations. Those are taking an in-person exam. But since you are doing it all online, you are taking still an exam on MyLab. Not you, because you are all online. So the final, everything, all the exams for in our class like are online. Yeah. So for better or worse, you're stuck with MyLab. So for this class, yes. Yeah. Everything like if yeah. If this class like the classes that happen to have like an in-person component, say either recitation or they will take like the an exam in like traditional exam for the next one. But for well, asynchronous, they're not. I think the asynchronous will still do it online, but I cannot comment on that because that's sort of run a bit differently from the rest of the classes. But I would make a guess that they're also online. I think, pretty sure. Well, the physicists, they always break their rules. But I mean, the policy for us, like our understanding was that if like the students were enrolled everything was online, like the recitations and lectures were online, you cannot really ask them to come to campus to take an in-person exam, But if you're at least in campus because you have to show up somewhere for either recitation or lecture, then it is sort of reason to ask you to take an in-person exam. But yeah, for this class, like, and you should only care about this class. So for this class, like the exam will the next exam will be in 3 weeks on November 15, and it will still be online. Yeah, and the final will be online and every.
Professor.
Yeah.
Yes. Wait, one quick question. Sorry, but was the third midterm on the 6th or the 7th of December?
Oh, the one that falls on Monday, I would say. So when is a Monday of those two? So it should be on the 6th because that's Monday. December 6th. Is it on the website 7? I meant this class. You should only care about this class, not this exam. Yeah. If it's like, it should say 6 because that should be on Monday. Is that okay? Good. Yeah. Well, hopefully, or you're saying that that's not. Oops. Yeah. I think December 6th should be on Monday, so that should be fine. Yeah. Good. Excellent. But yeah, so but we still have a couple of weeks to go. I mean, again, like for the next midterm is in 3 weeks, so probably like the information about it will be posted like by the end of this week or beginning of the next, like the announcement and the well, you should. I thought you were happy because of the concert yesterday of Snoop Dogg, so maybe that's why you're thanking him.
No, see, the thing is, like, always, even through high school and freshman year of college, there would always be like a math exam on my birthday, and I would be angry because I don't think anybody wants to sit there with an exam on their birthday. And so this time it is on the eve of my birthday, so I'm very happy.
Good. You see, no reason to game math then. Good. Well, no, that was corrected on the. I mean, if you go to the website, I have changed that. Like the website already says that it's November 14 for in person and 15 for online, I think. So it should be okay. It should say November 5th. Like I can I can show it. Like I can screen share this for a second to see if it's fine. If you go to here it is. In person and Monday, November 15 for classes with online lectures and online recitations. So the essentially it will be posted. I think what it will cover it will be probably announced next week, but it should be like Lagrange multipliers, which was 14.8, and most of chapter 15. Ending of like triple integrals. So, oh, um, I think like the practice exams and all of that should become available like in the next few days. So, but yeah, like somewhere around 15.7, I think that's where like triple integrals end. So it's like 14.8 to 5 through 15.7. But like yeah, you'll send like that will be posted as eventually here, like in a couple of days. Okay. Now, yeah. So what I was saying last time, let me remind you. So for now, we're doing double integrals. What that means is that you have a function of two variables, right? And you have some region on the xy plane. It is typical that you don't draw the graph of the function. So generally, you tend to draw only the region on the plane. You don't like plot it to see the graph of the function. So you draw like some region here R on the xy plane. And so we're trying to look at things that were written like this last time. Okay. And today I'll continue explaining how this is supposed to be computed. Maybe let me just make a couple of remarks because this can be a bit confusing. So what does this mean in general? What's the meaning of this? Like the meaning is that you're trying to do is that this is like some sort of sum. I mean, this is like the idea. Yeah, for yeah, for triple, it would be like I'll probably will talk about that next week or at the end of Thursday. But with for triple, you put like another integral sign and you put like dv instead of dA. So the meaning of this, like, I don't know if you remember when that I showed you this thing with the boxes, like approximating the volume of between the graph and the xy plane last time. But like this idea of Riemann sums. So really, when you think of an integral, what you think you're doing is like computing like a sum, like a sum of tons of terms, right? So this is really like some like the heuristic is that this is some sort of sum of the terms of the quantity because these are like the boxes, right? So this this is like the base of the box, right? And F here is like the height of the box, right? Okay, so so really what you're doing is like adding together f times the a. Okay, so but the whole point here is that actually this can give you different interpretations depending on how you think of f. So because like if this integral were only used to compute volumes, then like really it would not be that interesting. So think of this for example. So and then interpretation of f and what's the meaning of the double integral. Okay, so again, if you think of the function like, if you think that your function is really like some height, like, you know, the height above the xy plane, right? Then really this integral is computing something that's like height times area, right? No, chapter 16 is not won't be included. Yeah, that will not be included. It's like up to 15.7 roughly. So chapter like what is height times area, that's volume, and that's why you know, like, so this would be like sum of height times area, and this equals volume, right? So this is why in this case you say that the integral computes volume. But like, you know, there are other interpretations that are possible. This one is very common. Imagine that like the function f is really like f represents like a density. So it represents something like mass per unit area. So what do you think? What do you think the double integral would compute in this case? If you think of f as being like some density function.
Density is distributed within some volume, maybe.
Well, this is actually like a density. If it's because it's like a density of two, like a function of two variables. Imagine it's like the density of like a plate, a flat. You know, let me do like, imagine that you have like some disk or something like that, right, on the xy plane. And so you like, you know, I think people usually think of density as mass per volume, right? But you can also think about surface, that like it's some sort of surface density. So if you have like a if you have like just like a something like that's planar, right, like this thing that I'm drawing here, like you could imagine here like sorry, you could imagine like asking for the density of, in the sense of like the mass per unit area. Is that making sense? Like density doesn't necessarily need to be mass over volume. It could also be like mass over area, even mass over height, over like length. Like, you know, so like just think of it as like some flat piece of surface on the xy plane. So I'm telling you how much mass per unit area it has. Is that making sense?
So maybe kind of like the density of the curves, level curves.
Yeah. Well, it would be, in this case, it would be level surface. But like, think of it.
Yeah, level surface.
Yeah, like think of it like you have like a piece of coin, right? Like you have a
Yep.
coin, right? It is.
It's not the same everywhere.
It is like, imagine that it's so thin that for all practical purposes you only think of it as being flat, right? So like I could imagine, like you could imagine that someone gives you like the mass per unit area of the coin. If you sort of ignore the width, you know, so that it doesn't really occupy some volume. So it's more like, or if I give you like, this like, or imagine this thing, like maybe here is made with gold and here is with silver. And so this is like something whose like density would not be constant, but I'm just saying like, this is so thin that for all practical purposes, like when you idealize the problem, you just think of it as like, being like completely two-dimensional, right? Like you ignore the width. Is that making sense?
Got it.
So you just say, well, it's mass per unit area. Is that better? Or like,
That makes sense.
like there's like an analog of that when you have like a cable, if you have a cable, like you could think of like talk about like the density. That's actually something we'll do later in the class, but you could think of talking about the density along the cable, but that would be like mass per unit length, right? Because now you think of the cable as some like it's being twisted or bent, but it's sort of like just one-dimensional. So like the density can have like different like units, like in general. But if you think about this, like this would be like a sum of like density, right, times area. That's what that like the integral would compute, right? But like here the density is like mass per unit area, right, times area. So what do you get? What units do you get in the end? You get only mass. So this would give you the total mass of the object, right? So this is like total mass of the surface. Is that making sense? So in this is like a way in which you can use a double integral to compute the mass of something. You can also do it to compute like the charge of something, because then you can think that maybe like F is like the electric charge per unit area. It doesn't have to be like, there are different types of density, not just like mass per volume or mass per area. It could be like electric charge per area or things like that. So it would be like sum of density times area. But in this case, it would be sum of charge over area times area. And that gives you charge, right? Like this would be the total charge of the object. So you could imagine like, having like, this is like what people like, how TVs and other electronics work. Like there are these things called capacitors or things like that. I don't know if you have heard of them. Like they're like, I think they're like two parallel plates. And so you can imagine like having them electrically charged, and then like you just care about the charge per unit area. And finally, just to finish like these analogies, what if you think of f, like the function f, as just being exactly the constant number 1, right? Like what if f of x comma y is always the constant number 1? Right, so the function is always 1, right? What would happen if the function f is always 1? So this would be the sum of f is now 1. So you have 1 times area, right? And what does, like 1 times area, what should that be? That should be the sums of areas, right? And what is like, what would it mean to be the sum, like to sum the areas? That's like just the total area of the region R, right? So this is just the area of the, well, it's related to, yeah. So Calc 2 is sort of contained in what I'm saying right now. Like all of your Calc 2 is essentially a special case of what we're doing right now if you take the function f to be 1. That's what I'm saying. Yeah. In fact, like soon we will do some things that should look familiar to Calc 2, like with polar coordinates and things like that.
of a two variable function where where it's equal to a constant? Is that just like a plane in 3D space?
Right. Yeah, good. Like, what's the graph of this function? Yeah, okay. This is like the actual explanation. Like maybe if you have some region R, right? And you have like the constant function 1, right? So here's like the constant function 1, correct? It is a plane, as you're saying. And so what happens is that like there's like an exact clone of the region R above here, right? So you see, like there's like, if you think of in terms of the volume, right? It's sort of like if you had taken like the region R on downstairs and like you do like a sweep out. So you just move it vertically up, but you're moving it by the same amount in the vertical direction, right? So like since the height is 1, right? Like the things like numerically, there's not a difference between the volume and the area in terms of numbers, right? If the area gives you 50, if you ignore units, right? If the area gave you 50, the volume will give you 50 because like the height was 1. Is that making sense? So like that's the thing about mathematics, right? Like when one needs to understand, like there are really no units in math. So if you say that the function is constant equal to 1, like it's up to you to put the unit somewhere. But if you think of it like in terms of the volume interpretation, like what you're saying is that since the volume was always 1, if you get like volume equals 50 cubic feet, that means that the area had to be 50 square feet. You see, like because like there's like a conversion factor which is just equal to 1. So is that okay? So like this is why but what you need to keep in mind is that depending on what interpretation you give to f, like the integral always will be computed the same way. That's a nice thing, right? You'll see like then you always find it like the same way regardless of how you're thinking of this function. But like in a concrete problem, you need to think about what meaning you want to give your function so that that makes sense. So like it can be confusing because I have been telling you just like I told you last time, well, this double integral computes the volume. That's true when you think of f as being some height function, right? But if you think of f as a density, then it computes the mass, or we compute the charge. Or if you just think of f as the number 1, it would also compute the area. So like it's up to you to come up with the interpretation for f. Is that okay? So there are many things that fall into, there are many quantities that can actually be computed with double integrals, and that's just thanks to the fact that you can keep changing your mind about what f means. Is that okay?
Question to check like conceptual understanding, like an example. So if you're saying that like the vertical part of this integral can kind of be swapped out for different things, would it be appropriate to think of this like I had a metal plate and a hook in the middle and an elastic band pulling on that hook? Then I could like check the force across that surface on that plate based on like the elastic pulling on. Like, is that even close? I'm trying to move away from something that's just a height function.
Well, I just think I couldn't listen to you very well.
Okay.
Okay, you repeat again. I said I cannot. Like, I think if you like,
if you have a sheet of some material and there's a force pulling on it, like an elastic band that's hooked onto that surface, would this be something that like you can calculate some sort of like tension force pulling on that surface?
Oh, right. Okay. Now I get it. Like if you exert some sort of force on the surface, you mean?
Yeah.
Like, yeah, like you, like, right. Like you could imagine like, Good, good. I think I get what you're saying. Right. Imagine that you have like, oh, this is Bed Bath and Beyond. If someone needs a coupon, so you're applying a force, right? But like the force that's being applied is not constant, right? It changes on point to point from the surface, right? But maybe you want to compute like a total net force applied on the object, right?
Perfect.
Then you need to do like an integral, but really like the function that you would be given is like how much force per unit. Okay, it's like the pressure stuff, right? Like pressure is like force per unit area, right? That's a good example. Everyone remembers this? Pressure equals force per unit area, right? So pressure times area equals force, right? So you could have like a plate, right? You could have like some plate or something two-dimensional, and you have like a pressure function, right? So F is like the pressure exerted at the point X comma Y on the plate, right? And then like the integral of the pressure will be like the total force exerted on the plate. Is that, I think that's what you.
Yeah, no, yeah, the example of trying to get at.
Is that okay? Good. Yeah, but right, like, or tension or other things, right? Like, yeah, like, so there are many quantities that fall into this category that can be analyzed this way. But I just bring this up because sometimes you'll see problems that ask you, like, they tell you F is like some density, find the mass or things like that, and this is how you're supposed to do it. Like you just do the integral, but like maybe now it looks more clear why that makes sense. Now let me give you something important, which are the rules for finding integrals. So this is what I promised last time. Rules of the game. So there are like two. For now, we'll diversify what we're doing very soon. But for now, there are two things that we're doing. If we had like a region R, we were breaking it either into vertical cross sections or horizontal cross sections. I don't know if you remember that from last time. So let me draw the picture again. So one thing that we were doing was like vertical cross sections. I like to call them, like, think of them as arrows. So one thing we were doing we're like using vertical arrows, which you would draw from moving from south to north. Okay, so they move from south to north. Okay, sorry. Let me write it again. So yeah, vertical arrows are also called vertical cross sections. Also called order of integration dy dx. So this is the other way in which it's called order dy dx. Okay.
Are the problems for this going to be like word problems, or will it just be like something's given and you just have to solve for it?
I mean, they're not word problems per se, but the region typically, I mean, like it's more like the region is described maybe in words, right? And then you have to figure out the bounds. Like in these types of problems, like the real important thing is to figure out the bounds that you have to put like in the integral. So it's more so it's not that it's necessarily in a word problem in the sense that you think of word problems like for optimization, right? Like where they tell you you're like doing like a box and you want to maximize something, or you just want, like, you know, that there's like an entire plot line to what you are supposed to find. But you'll see the examples that I'm about to do, they're like close to what you should expect, like where you like a region is described by certain equations, curves, or whatever, and then you find the bounds from there. Okay, so if like the idea is that since these are vertical arrows, right, like they were parallel to the y-axis, so when we do the integral of a function, the thing that will appear first is the y. And here you put in the second one that you write is the x. So you see, since we are used to reading from left to right, this is what is called dy dx, the order of integration dy dx. And in this case, like the bound that you put here, you write the curve where the arrows start. And again, like in a second, like it will be clear. And on the top, you put the curve where the vertical arrows end. Okay. And so these two can be functions of x. So here the bounds, let me say that also. And in the last, so that's all for like here in for the first thing that you put. And for the one on the outside, for the integral on the outside, it's just like you put the smallest value of x, and here you put the largest value of x. So that one is not too bad. So here, like the bounds are only constant numbers. So the bounds are only numbers in this case. Okay. And again, I'm about to do an example where you'll see both methods, but let me write the other one next to it. So the other alternative that we discussed was like to use horizontal arrows, right? So these travel from west to east. Okay. And they're also called horizontal cross sections. And they're also called the order of integration dx dy. So they're also called order dx dy. And so it's similar. Let me put it like this to what I just wrote. But now since the arrows are parallel to the x-axis, the first integral that you do is with respect to x. And it's like an analogous story. So like the bounds that you put on this side is where like here you put like on the lower bound, you put like the curve where the horizontal arrows start. And on the top, you put the curve where horizontal arrows end. And on this, on the inside, like the bounds can depend on y. And likewise, the bounds for the one on the outside are just easier. Those are just the smallest and largest values for y. Okay, so here is just.
So, will we be given like differing levels of boundaries in the problems that we're given? Like sometimes we'll be given all 4 boundaries, other times we'll be given 2 and have to figure out others.
Yeah, it like it's something that like it will be more clear once I start doing some more examples, but typically it's like the region will be obtained like either like by intersecting some curves. Most of the time it's like 2 curves, but sometimes you'll maybe if it's like more like a rhombus or like a parallelogram, there would be like 4 curves, right? But yeah, I'm about to do it like an example that shows like how this is done. It's not that you have to find the region R, but you do have to find the bounds of the region R. So the region R is always a given, but from the picture, you sort of have to figure out the bounds, which is why I was saying that this is what people tend to find tricky about integrals, because like finding the bounds is like not so like algorithmic, right? Like, for optimization problems, well, you find the derivatives and then equal to 0. That's like an algebraic problem. But finding the bounds is just like from the visuals of the region, you have to sort of read the bounds. So it's like more, this is more like a spatial, when people talk about different intelligences on the brain, like this is more like spatial intelligence. The other one's more like algebraic or in linguistics even. So let me do some examples so that you see how this is supposed to go. And again, like to a large extent, the difficulty of these problems is actually to find the bound. So let's just work on that for a while. So let's say that the region R is a region in the first, is a region this is more or less how you would expect to see the problem written. Like the region is typically presented in this way, like just by giving you some curves. If the curves are not hard enough, then you are supposed to draw the picture. If sometimes if the curves are sort of complicated, then the picture may be given to you. But like there are like certain curves that you're supposed to recognize. So for those, like maybe you're not given the picture. So let's, I don't know, anyone remembers how the graph of square root of x is? It's something like this. Okay. And then what's the graph of y equals x squared? It is something like this. So you see there's something that got trapped between the two curves, and that's what we are referring to as the region R. Is that making sense? So how would you set up the integral if you wanted to do the vertical arrows, right? So let's try to do first the vertical arrows. Again, this is also called the order dy dx.
So then would it be x squared minus, actually no, root x minus x squared?
Well, you're not supposed to subtract them, but like you found the right curves, but you have to, it's close to that, yeah. Let's see. Sorry, back
Or
here.
would it be an integral of y from the boundary of root x, I mean x squared to the boundary root x?
Yeah, that's correct, yes.
Okay.
Because like, this is where one does not need to panic. So just take a breathe some air and just think about the rule, right? So you draw some vertical arrows in your picture. That's what you're supposed to do. So you draw them here, and then you look at the recipe. So the recipe tells you that the bounds that you should write are the curves where the arrows begin and the curve where the arrows end, right? So, and again, the arrows move from south to north. So on which curve, like there are only two curves on this picture, right? So on which curve did I begin drawing the arrows? I started on the brown curve, correct? Is that making sense? Right, and that has equation y equals x squared. So you're supposed to put x squared as the lower bound. And where do the curves terminate? They and or you stopped drawing them where they hit the orange curve, right? And so then square root of x. And this is the most crucial part. If this is okay, like you're sort of like figuring out like the hard part of the problem, which is setting up the bounds. So is this making sense? Like how I chose the bounds here? And then you see like the bounds are correct in the sense that it respects the rule that I wrote. You see like I told you here, the bounds can depend on x. So like the bounds here are allowed to be functions of x because like x is still not being integrated. So then what you're supposed to do for the bounds for x is just find the smallest and largest values that x takes on this region. So how small can x become on this yellow region? Yeah, good. You have to, it's 0 to 1 because these two curves intersect when x equals 1, right? Is that okay?
Sorry, is that a negative in front of the square root, or is that just a bracket?
Good.
Okay.
Good, thanks. Now let's try to do like, this is maybe the one that tends to be a bit more confusing. Let's see how the horizontal arrows behave. And again, this is also called the order dx dy. And well, you could draw the picture again, or you just draw the arrows now horizontally. Well, almost there. Okay, good. Let's think about this for a second. So this starts is it okay? The horizontal arrows begin like now you're moving from west to east, right? So where do I draw them first? I draw them on the orange line, right? But that's the thing, you have to solve for x now. So this equation could also be written as x equals y squared, right? So I have to put like the equation like in this format. So I put here on the bottom y squared. Because remember the rules of the game. The rules of the game is that now that the bounds can be functions of y, if you think about it, if you go back. Because essentially the bounds can be functions of the variables you're not integrating. That's that's what's going on here. And where do the arrows, like the horizontal arrows, end? They end on this brown curve, right? And yeah, as was pointed out, the equation of the brown curve is x equals square root of y. Is that okay? Is that making sense? Good. And finally, the last one is like, well, the last variable to make, or the last integral to do, is like the easiest one. You just have to write the smallest and largest value that y takes on this region. So how small can y become? Yeah, it goes. This one still goes from 0 to 1. It's a coincidence. Like you'll see in the next example, like it's not that if it's 0, 1 for one of the integrals, like it's 0, like 0, 1 in the other one. So I mean, it was just like a coincidence that it was 0, 1, 0, 1 in both. Like they could be different numbers, but the point is that they have to be numbers. Like these bounds can only be numbers. They cannot be functions anymore. This one.
Question. And this is kind of stemming from Calc 2, when we had to find an integral, but it used two integrals to find an area of a region because it was some weird region. Would we have to use two double integrals in this case?
No. So like, oh, well, I mean, like the next example that I would do is one where like you have to break it into pieces. I don't know if that's what you're referring.
Yep, that's exactly what I meant.
That's where we're going. Now, well, this is a good, like in this particular case, I didn't give you like any expression for f because like the thing to like wanted to emphasize is how to find the bounds, right? So for a concrete problem, in order to finish doing this, like you would be given like a particular expression of f, like x plus y or x times y squared. But the point is that like whatever the function is, that's separate of how you find the bounds. The bounds are found the same way regardless of which function you're given. In fact, you'll see like there's sometimes some problems which are just like write the bounds because just to test your like abilities to do that. But you see like this is why the flavor of these problems are a little bit different, because like you just have to start drawing things and see like which curves you get. So some people prefer that and others do not. So well, no, there will be a couple that will, I mean, probably there will be some that are just writing the bounds, but there will be others that will, after writing the bounds, will ask you to do the integral. But for now, we're just like getting used to finding the bounds because that tends to be the hard part for many of these problems.
In a previous section, I remember we've like flipped all the variables to one side and set it equal to 0 and say that that's a function of those variables. Yeah. Like if we rewrote the first Brown equation as 0 equals x squared minus y.
Right. I see what you're saying. Like you could write like I agree. You can write the Brown equation as y minus x squared equals 0, right?
Right. So I see like we're integrating functions of x and y. Like does that sort of algebraic maneuver come into play? How do you actually get the function of x and y?
Oh, like you
we haven't finished this, I guess.
Well, I mean, yes, I know. Well, like just to comment on what you said about y minus x squared equals 0, right? If you write it this way, you're writing it as a level curve, right? For the function y minus x squared. So this is all consistent. It's not really that necessary in this context to think about it this way. Right, strictly speaking, the problem is not done because I haven't given you like a particular function for f. The reason why I didn't do it is just to emphasize that the point that finding the bounds is independent from doing the actual integration, right? Like the bounds, like these bounds are like universal in the sense that they depend only on the picture, right? Regardless of the function f that I give you, you would use the same bounds. That's what I was trying to say. Like in practice, right? Like you would like need to be given like a particular function if you actually wanted to find to conclude the problem. Is that making sense? But this function f also is completely unrelated to whatever function you could get from like these curves, right?
Perfect. And in a problem, either we'll be given that and it will be relevant, or
right.
It may be left out.
The problem would either be like write the bounds, because there are problems which are just like this, like just write the bounds, or other problems which are like oh, okay, and then for this particular function, like do the integral.
Okay, got it.
Yeah. Is that okay? The thing is, like, you know, this is similar to like the chain rule, where like it takes time to get used to it, right? So like the best thing to do is like just do like a bunch of examples so that one starts like noticing patterns. And integrals will be with you until the end of the course. So like essentially now all of the class will, like double and triple integrals will just keep appearing and appearing over and over. So like after one reaches like a certain threshold, like this becomes a little bit more natural. Well, no, but they're like fun.
Does this become like derivatives?
Sorry.
Would this become like the way we use derivatives?
Well, it's always, I think integration is always less natural. Like, so it will never become as mechanic as like finding derivatives, if that's what you're asking me. But they're like certain, like, but it will be like eventually you'll spend less time like finding the bounds, right? Like there's some learning curve to this, and like after a while it will take you less, like, you know, you'll make like less silly mistakes, quotes, right? But I do think there's a kind of symmetry. Derivatives, in a sense, they're always easier to find than integrals, because like at the end of the, like even like think about it, like on Wolfram Alpha, you go to Wolfram Alpha and you just ask Wolfram Alpha to find the derivative, right? Wolfram will do it. If you go to Wolfram Alpha and like ask Wolfram to find the region of integration, I'm pretty sure Wolfram cannot do that in most cases. Like if you just wrote like in words, region of integration, right? Find the bounds. I think that's not something AI has reached. So you're still doing like non-AI problems. It's still a bit like this. Still is a bit trickier, but like it will get better with time. No, there are no series in this class. So, but they're like double series. I mean, there's like a notion of double series as well. Yeah, you can like, right, like you can still use Wolfram to find like the intersection between the curves and things like that. No, there are no limits. Limits are over. They're dead. There are no more limits. So let's do another example. Good. Let's do a triangle. Now the region is a triangle. And again, like maybe think of it as being given to you in this way. So now the region is a triangle, like the inside of a triangle. Whose vertices are the points -1, 0, 0, 1, and 1, 0. Okay, so let's try. And again, that may be all the information that's given to you. Okay, and from there you have to draw the picture and then start finding the relevant information. Like sometimes more will be given, but like this is sort of like the minimum information that you could receive. So right, those are the three vertices of the triangle. So you complete it. Oh, let me in fact complete it using different colors. So we were using brown for here. Let's do orange here. And let's do another one. Oh, let's use green here. So what's the equation of the green side? That's the easiest one, right? What's the equation of the green side?
Y equals 0.
Good. Y equals 0. What about the brown one? This one.
Y equals -x plus 1.
Yes. Good. And minus x plus 1. And how about the orange one? Yes, y equals x plus 1, correct. And again, like strictly speaking, you could find these equations like using finding the slope first, but like if they're relatively easy points, like you can sort of also do it by hand, you know. But yeah, like one way was like, oh, this is a decreasing line, and like the intercept is 1, and from there it's almost ready. So, and like let's try to do the same as before. Now you'll see that there's a small difference here. So let's see if I can do this. Let's just for to turn things around, let's start with the horizontal arrows. So let's do the horizontal arrows first. And again, this is the order, the x, dy. So literally draw horizontal arrows. So let's do that.
The arrows always go left to right and bottom to top.
Yes, they always go in the direction of the increasing coordinate. So the arrows are moving where x increases, right? So x becomes more positive to the right. So that's why the arrows are moving from like west to east or left to right. Yeah.
Thank you.
And like for triple the coordinates, it will be like, you know, from south, like, you know, but like from the floor to the roof once we have like a third axis, because they will move in the direction of increasing coordinates. So okay, so you asked the same question, where on which curve do the arrows begin? Where did I begin drawing the arrows? Right, so which is the first curve that they touch? They touch the orange curve. Right, but here you have to be careful, right? Like the equation is the orange curve, but x has to be given in terms of y, right? X has to be given in terms of y. So yes, it is x equals y minus 1.
Don't you have the dx and dy flipped? Wouldn't the dx be on the outside?
Sorry?
Wouldn't the dx be on the outside and the dy be on the inside?
Well, that depends on which arrows you're using. Like we're doing both cases, but here I started with the horizontal arrows. So you see, like I said that I was flipping things around, right? The order in which I was solving the problem.
Yep.
So like the x, like you should think about it this way, that horizontal arrows are parallel to the x-axis, right? So that's why I put the x, the
You're
x.
right.
Yeah, good. But like this is also good because it causes confusion because like maybe you're just right. You're just well, sometimes you're asked to use a specific order, or sometimes you're asked to write it in both ways. So both possibilities can occur. But obviously for us now, we're interested in doing it both ways so that you can compare, you know, how to write it. But yeah, on occasion, it may just be asked to do it in one specific one. And yeah, someone said on the chat the arrows end on the brown one, but again, the brown one needs to be given in terms of y. So it's yes. So if you solve for x here, you get 1 minus y. Because again, like remember the rules of the game are x can, like the bounds here can depend on the variable that you're not using to integrate. So the bounds are allowed to depend on y. And then for y, you have to put the smallest and largest value y takes on this triangle. So what's the smallest value for y? And what's the largest value for y is 1, right? And then, so far so good. Any questions up to this point?
In the other case, would it be kind of like using the symmetry because it looks like it's an equilateral triangle?
Here's the thing, like people are always have like the temptation to use a symmetry, and that's fine if you knew that the function that you were given is symmetric, right? The thing is that here you don't know anything about the function itself, right? So the function could actually spoil the integral. So it's not that you're like, for example,
Okay.
yeah,
I see. I see.
good.
I see.
Yeah, don't fall for the it's like if you computed like the mass of a person, right? Like
Yep.
you say, well, there's symmetric around the nose or whatever, but maybe like the mass distribution is different, right? Because like the heart is on one of the sides and etc. So yeah. Well, it depends on the particulars of the problem. If the function is symmetric, then you can like split it into two, but like that's not what I'm trying to do in this example. So what if you were trying to do like use vertical arrows? So again, this is called order the y dx. So I start drawing vertical arrows here. And now what do you realize is happening? There's a fun thing that's happening.
You're gonna have two double integrals, one going from -1 to 0, and then the other one from 0 to 1.
Right, because you see, like for these vertical arrows, where they all start on the green line, right? All the arrows, regardless of on which side you are, they all start on the green line, but where they end, it could be either on the orange line or the brown line. So you have to break the integral into two pieces to set it up correctly. So is that making sense to everyone? It's just because, like the termination, like where they terminate they can terminate on different equations, right? So let's look first on this side of the triangle. If you just look at the part of the triangle, which is on the second quadrant, right? Where do the vertical arrows begin? The vertical arrows begin at y = 0, right? Where do they end? They end on the orange line. So it's x + 1 here. And again, this is fine because remember, like the bounds for this integral can depend on the other variable. So it's fine to have bounds here that are functions of x. And so what values for x should you put here? Well, you're only working with half the triangle. So the bounds for x should be from -1 to 0. Is that okay so far so good? Is this half triangle fine? Okay with everyone?
Yeah, all good.
Good. And then the last one is similar. The other half is similar. Like, where do the vertical arrows begin? They begin when y = 0. And where do they end? They end and -x + 1. And then the bounds for x are now from 0 to 1, right? Is that okay? Is that making sense?
Yep.
Good. So like this is telling you something also, that you see some regions are more friendly towards one of the orders, right? Because in the first case, like you only needed to write like a double integral, but if you wanted to use vertical arrows here, you're forced to do 2 double integrals. So there are regions which are more adequate for like certain orders of integration, right?
What if it was a circle?
Oh, well, circles we'll do next time, actually.
Okay.
Yeah, popular demand, because I think circles are like becoming very, I mean, I can tell you something quickly if you want, but like really circles will be done with polar coordinates. So, but just quickly, because like this is not the right way to do circles, but like I can explain it if you want. Like if you have like a circle like this, right? Say if you want to use vertical arrows. So this is like an aside. Let me put it separate from the rest. If you wanted to use vertical arrows, well, the thing is that you have to solve for, you would need to write y equals plus or minus square root of 1 minus x squared, right?
So 2 half circles essentially is what
Yeah,
you.
essentially, you think of it as 2 half circles. So you would
Okay.
do like from -1 to 1, and then from minus root of 1 minus x squared to root of 1 minus x squared, something like this. Is that making sense?
That's nice.
But again, this is a bad way to do it, like in a sense. So this is not how we're doing it. We'll do it in polar coordinates next time. But that's like, and like you see,
Yeah.
like, the other one is sort of, I mean, you could do it horizontal arrows, but then you just solve for x in terms of y.
Mhm.
Everything
Yep.
else. Yeah, good. Now, this is a cute one because now you see now the function actually makes a difference. So this was an aside. And
Oh, but then if you use polar coordinates, then you could just use the formulas for the arc lengths, right?
well, arc length,
Kind of like it would be like an integral of the arc lengths. That would be your.
it is this thing that r squared, I mean, you'll see it come up, but it's not, well, I don't know if you want to call it necessarily arc length, but it would be in terms of theta and r, right? So you'll say theta goes from 0 to 2 pi and r goes
Yep.
from 0 to 1. So
Yep.
that's
Okay.
going to happen. But now, like, since we haven't done any examples with a particular function, now let's do it. And you'll see this one is interesting because of something nice that happens. Let's say that the function is this one, okay? And the region, okay, no, I have to do it. Oh, yeah, I have like, yeah, that's fine. Let's say I will use this function and the region of integration is our friend, the triangle. So let's say you want to integrate this function over this triangle. So it's like the vertices are 1, 1, 1, 1, 0, and 0, 0. Okay. Now, how would this look if you use vertical arrows? Okay, let's put the function inside. What bounds should I put for y? And like, by the way, it's very common, like for people not to put the parentheses after a while. So usually people won't write like a parenthesis like I have been doing. So like this is more like a normal notation for the integrals. So it's good to write it now like this.
Be from 0 to x.
Yes, it would go from 0 to x. I agree. The arrows start at the bottom, so they start on the x-axis, which is y equals 0, and they end at the equation of the hypotenuse, which is x. Good. And then the x. What are the bounds for x? They're just from 0 to 1, right? Is that making sense?
Yeah.
And so again, well, remember when you are integrating first with respect to y, x has to be considered a constant, right? So what is this integral with respect to y?
0.
You're integrating, okay, this is like
Isn't just a constant, so you would just,
what, right? It's not
oh,
the
it would be
derivative of
this times the constant, so this would be like sine x over x times y.
yeah, right, good. Yeah, good. Is that making sense with everyone? Because right, like this is like pi, and so remember, like in integrals, pi is like that, and so when you do that, you get the integral from 0 to 1 of sine x over x times x minus 0, which is x, so the x. So this is the integral from 0 to 1 of sine of x dx, and what's the integral of sine? That's negative cosine, right? And so that's the answer for this integral. Yeah, you have to be like it's good to do an example where you are also integrating so that you don't forget the rules of integration. But is that making sense? Now, what would be the integral if you had tried it that in the opposite order, right? What would you have needed to do if you had tried to use horizontal arrows? And we're almost done with this. So what if you wanted to do horizontal arrows here? What bounds would you put first for x? You have to put now where the horizontal arrows begin. Where do the horizontal arrows begin? Yeah, they begin on the hypotenuse, which has equation y. So you put here y, and then they end at this vertical segment. So they end when x equals 1, and the y values are 0 to 1. Is that okay with everyone? But now here comes the interesting fact, like now you have to integrate these functions, like this stuff first with respect to x. And what's the integral of sine of x over x with respect to x?
Cosine x over x squared.
Well, if you think that's the one, that means that if you took the derivative of that, you should get sine of x over x. And I can assure you that won't give you sine of x over x. Well, the answer is that there's actually no known formula for that. You're stuck. So you stop, you cannot do the integral. There's no like obvious antiderivative for sine of x over x. So you cannot keep integrating it, even if you set up the integral correctly, right? So the problem here is that we don't know, but we don't know how to integrate this. Oh, that's a good thing. Yeah, well, I mean, you could do like a power series, for example. You could write sine of x as a power series over a Taylor expansion, and then you try to see if you can justify integrating like a power series. Like there are formulas in mathematics for doing integrals of power series, but like there are other things you need to check. It's not yeah. But I mean, if you play fair and square, you're stuck. But we know that the answer has to be 1 minus cosine of 1 because they are the same integral. They're computing the same thing. So this is an example where by switching the order of integration, you can actually do the integral. Okay. So we saw an example where like an order of integration might need a double integral and the other order might need two double integrals. And this is an example where with one order of integration, you can do it for a particular function, but with the opposite order of integration for a particular function, you're just stuck, okay? So almost everything under the sun, anything under the sun will happen. And you can always come up with examples where like one thing works better than the other and stuff like that. So like what we're going to do on Thursday is move towards the world of polar coordinates. So we'll talk about polar coordinates, and then next week we'll start probably with triple integrals. So we'll do color next.
This might be a stupid question, but really quickly, for this one, if you split it into, say, the integral from y to 1 of sine x and the integral from y to 1 of 1 over x.
Oh, you mean like split it as a product of two integrals?
Yeah, can you then compute that you get, you know, cosine x and then ln of x?
Yeah, no, yeah, but like actually this is actually related to one of the conceptual problems that I gave for next week. In general, you cannot, you know, like a double integral cannot be broken into a product of subintegrals. So
okay, got it.
yeah, you have to do like, it's not like this. It's not like a multiplication of integrals that you're doing here. You really need to do the one on the inside and then the one on the outside. It doesn't work if you sort of do inside times outside in some weird way. Yeah.
Okay.
Yeah, but like that's a thing to try, let's say. But yeah, it won't work. Yeah, good. Okay, I'll see you on Thursday then.
Have a good one.
Unless someone else was going to do something or.
Thank you. Have a nice day.
You too. Well, if someone wants to, like, you can email me about the letter grades if you want to. Someone had a question about their letter grades. I mean, in general, like, usually the classwork probably will help. Like, you know, typically people will get most of or all the points on classwork. That tends to help your overall grade. But right, like from the exam letter grades, like the idea is to start to try to start drawing a pattern. But yeah, usually it's likely that either with the help of the classwork, your letter grade remains close to the exam grades or just like increases by 1. Like say you go from D to C or depending on how, or C to B, depending on how close you were to B. So, but like the letter grades should somehow be like some sort of good indicator of the exams. Yeah, but yeah, good. Perfect. I'll see you all next time then. Bye.